right, let's jump into today's lesson. This is actually the capstone lesson of the chapter. This lesson puts everything that you've learned about transformations together and then converts it into proofs. And when you say, oh, I hate proofs, you've been doing these type of proofs since you were probably 2 years old. You just had no idea that you've done this type of proof before. So what are the methods that we've used to show triangles are congruent? What is one of the methods that we've shown triangles are congruent? SAS. What's another one? SSS. Another one. ASA, AAS, and HL. Those are the ways that we've shown that triangles are congruent so far. I feel like we have something else. Isn't there something else that we learned? No, that's showing that parts are congruent. I thought there was like another chapter where we learned something else. Maybe not. Okay, so those are the ways that we have proved that triangles are congruent. And ways that we've shown that triangles are similar was AA, SAS of similarity, and SSS of similarity. And these are like 2-column proofs, basically. We're going to learn a different way of proving figures are congruent. So for people who are at home, you don't see this, but on my board, I have a figure that looks like this. And then I have a figure that looks like this. Close. And they are currently on the board. One of them is taped to the board. This one is taped to the board. And the other one is just sitting there attached with a magnet. Now what I'm going to do is ask, can anybody show me that those are guaranteed to be congruent? BA, you want to do it, don't you? Can you go up to the board and show me that they are definitely congruent and do a 2-year-old's proof on this? Wow. Look at that. Okay, so once again, fantastic. The student who's in class right now proved that they were congruent, and all he did was go over and get this, and he rotated it slightly, and then he shifted it on top of it. And anytime a figure can fit on top of the other figure, then it's going to be congruent. Now think about, what did he actually do? When he picked up the paper and he did this, what was that called? A rotation. So he did a rotation. What do we know about a rotation? It is it's a transformation, and it's also an isometry, which means after he went over and rotated it, it's still congruent. Then once he rotated, he went over and did what? He went like this and shifted it on top. He translated. And what do we know about a translation? It's an isometry as well. So if he did an isometry followed by another isometry and it sits on top of the other one, then they must be congruent. And we know that. If you do isometries back to back, things don't change. So that is basically the proof. It is rather easy. It is basically 2 figures are congruent if and only if there exists a set of isometries that maps the figure onto the other figure. If you can use rotations, translations, and reflections, and you can get a figure from wherever it is on top of the other one, then guaranteed they have to be congruent. Like I said, you've done these proofs a million times before. You just didn't know what a translation was, a reflection was, and so on. Now let's adapt that slightly though. So now if we want to show that things are similar, it would be a set of isometries. So I'm being lazy and efficient in doing that. It's the same as up there. There's a set of isometries and a what? If I'm trying to prove that like this figure is similar to this figure, I would go over and reflect it, I would translate it, and then what would I do? Dilate it, and a dilation. Great job. A set of isometries that maps a figure, so it'd be isometries and a dilation that maps the figure to the other. Okay, so let's take a look at this right here. If we are trying to go from the LMN to this one, we're trying to prove that this figure is congruent to this one. So I am starting at 1, then I'm going to go to 2, then I'm going to go to 3. Let's go ahead and write the instructions that would prove that this thing is congruent. What does it appear that the first one is? A rotation. This is going to be a rotation of some number of degrees. I need to go up to the board real quick and measure that. All right. So that was a rotation. I just went up to the board. That's a rotation of 90 degrees. Around what point? 90 degrees around P. P is over here. O is that point right here. Okay, that is going to be followed by what? What seems to happen then? How do we get from 2 to 3? A reflection over line N. And those two things will map the figure 1 onto, that's supposed to be figure 3. And bingo bango, that is our proof. You guys are used to doing 2-column proofs where you're using the reflexive property and alternate interior angles and all that jazz. This is just saying, what are the instructions that would lead to get this figure on top of this one and then this one on top of that one? And what is the whole path? Does anybody have any questions on that? Hey, I got a question for you. I know that they went over and showed you this, like the actual steps that were happening, but how many different paths could we get from here to here? A lot. Imagine this. If I took one of our students that's in the room right now and I went to the other building and I did like a chalk outline of them, and I wanted to prove that their body was congruent to the chalk outline. Well, how many different ways can they get from here to there? Well, they can go directly there. They could go over to Dutch Bros, get a coffee, do a few reflections on the ground because they're so hopped up on caffeine, and then there's infinitely many ways to get from here to here. So how many answers are there? Infinitely many. Okay. When they go over and draw it out, though, they're asking us to figure out exactly what they're doing. So let's look at this one. It's obviously going black to red to blue because you can see your primes. So what is the first thing that is happening? It's being reflected over what? Y-axis. Great job. So reflecting over the y-axis, we'll take it from the black to the red. And now it's going, what I usually do is I'll get that point on top of this point, and then I'll like do my dilation from that point. But you can see here that they're going over and dilating from 0. It's like stretching out. So we need to figure out how much are they dilating it by. Are any of these side lengths easy to measure, or are we going to have to go over and use the distance formula? Anybody? Distance formula, that sucks. I don't want to do that. I don't feel like doing the distance formula. Let's try to do this a different way. Since we know it's from 0, 0, let's just look at the points. The point first was at 1, 4, and now it is going to, that's no bueno, right? Does anybody have any idea what that is? I have no idea. You see how it's not the perfect location? So we can't do that one. How about this one right here? What is that at? -4, 2, and then where does it go? That looks like a pretty point. Please be a pretty point. I think it is. Goes to -6, 3. Okay, let's just check if this is a dilation centered at 0. If it is, it's obviously getting bigger. So we have to check, does -6 over -4 equal 3 over 2? Do both those things equal one another? They do. Okay, fantastic. So that means that we didn't have to look at the side length. Remember, you can look, if it is centered at 0, 0, you can either look at the side lengths or you can go over and look at the points. So in this case, this point was F and F prime, or F prime and F double prime were good. D and D, or D prime and D double prime looked to be good. These ones were not because it was like a weird fractional point. But anyways, it's going to be a dilation. What is the scale factor? It's getting bigger. Is it 3 over 2 or 2 over 3? 3 over 2. And where is it centered? At the origin. And since that goes over and maps this figure onto that figure, they must be similar. And this is your proof right here. Hey, just do this. What I'm going to do on your homework is I give you like 5 different options. And I say, which ones of these are proofs to prove that the figures are either congruent or similar? Does anybody have any questions on that? Friendly little reminder about these. If you go over and you want to rotate by 90 degrees, it is flip it and negate the first. The other one is leave it and negate both. And this one would be flip it and negate the second. So this says, write a composition of rigid motions and a dilation that would map the RST to the other one. I'm going to zoom in just so we can see it a little bit better. We need to make sure that R matches up. R needs to match up with P. S needs to match up with Y. Okay, it appears that we could do this in two different ways. How can I get this figure like over into this quadrant over here? There's two different ways. One is, not one, because one reflection is going to switch the orientation. Like if you were saying go over this diagonal line, that's not going to work. It would be what? Okay, we can do one rotation. If you guys want to do a rotation, we could do a rotation and then we would do our dilation. What is the same thing as one rotation? What did we learn in yesterday's lesson? Two reflections. Okay, you guys tell me, do you want to do one rotation of this thing or do you want to call that two reflections? I don't care. I think it'll end up at the same place. Two reflections? Okay, cool. Let's do that. We are going to reflect first over the y-axis. Then we're going to reflect over the x-axis. And if I did that, the point would be here. Or not the point, the triangle would be here. Now, does it look like we can dilate from the origin to stick it on top of this other one? Does it like grow outwards from the origin? It does. Okay, so let's just make sure. This is the point, -1, -1, and the other point is -2, -2. If you put the x over the x and the y over the y, do you get the same exact number? Yeah. So this one would be followed by a dilation. Scale factor, it's getting bigger. 2 centered at the origin, 0, 0. You could also look at the side. The side length is 2, and this one is 4. That is one of them. What is a different thing we could have done instead of those two? Let's write a second proof. What is a different way? How many degrees is this being rotated? 180. We could rotate 180 degrees around the origin. And once we do that, then we could follow it up by a dilation scale factor of 2 at 0, 0. Anybody have any questions on that? You also could have done this. You could have gone over and done a rotation of 180 degrees around 0, 0. You could have then done a translation. I could translate this point onto this point by going left 1, down 1. And after I did that, then I could dilate by a scale factor of 2. But now, since the figure is sitting right here, where would I dilate from? Would I dilate from 0, 0 anymore? No, I would dilate from, it looks like, -2, -2. What I'm getting at here is this is 3 possible proofs right here. How many more exist? Infinitely many. So that's why this is a nightmare for me to grade when this is on a test. That's why I'll give you like 3 options and say which ones work and which ones don't. On your homework, you have to do both. You have to do which ones work, which ones don't, and then you do your own. What I want you guys to do is I want you to do this. Let's be on the same page though. I want you, rather than dilating from 0, 0, let's go ahead and after you do, does everybody see we're going to end up reflecting? Okay, we're going to reflect and then let's match up this point with this point. Okay, it looks like you're going from the big one to the small one, going from big to small. You know that you're going to do, what is going to be the first thing you're going to do? You could, I guess you could, couldn't you? You could dilate centered at C, and then you could go over and flip it from there. I kind of want everybody to somewhat do the same thing so we can at least check our answers. Wait, that's an ugly number, isn't that? Okay, so we don't want to match up those ones. Okay, so don't shrink from here. What I want you guys to do is I want you to shrink from here first. So let's do a shrink first and shrink from B. And after you've shrunk, Then what are you going to do to get over to here? Shrink it, then it looks like you have to flip it, reflect it. And then after you've gone over and shrunk it at B and reflected it, now it's going to be over here, and you're going to want to match it up with here. What is the process going to be after you shrink it and flip it over to this other side? Translate. Okay, I want everybody to do this one, this proof. Shrink from B, figure out your shrink from B, then do a reflection, and then do a translation. This way we'll all match up. People at home, pause the video, do it on your own. Okay, so once again, you could do this in any order that you wanted, but you guys decided let's shrink it first, then let's reflect it, then let's translate it. Okay, cool. So we're going to shrink it, which is a D, and we are going to shrink it. We see that this side length right here is 4, and we want it to be 2, which means we need to shrink it by a scale factor of 1/2. And you could have shrunk it wherever. I know that B is closest to what I'm going to be reflecting over, so I decided that I'm going to shrink it at B. So I'm going to shrink by 1/2 centered at B. And that makes it like this, and then goes over by 1. And I think it looks like that. Does that make sense? Okay, so now we are there, and we are going to reflect it. Get some blue. We're going to now reflect it, and we're going to reflect it over the y-axis. When I reflect it over the y-axis, it's like this, I think. Now it's there. It's almost on top of itself. I now need to translate it so that the blue one is on top of the other one. If I do that, that is going to be a translation. Which I'm going to match up this point with this point. So how much left and how much down did I go? Left 1, down 1. And there you go. This is one of the infinity proofs that you could have done to prove that the big figure is similar to the small figure. Any questions on that? See what else they got in store for us. I think it's just I put a bunch of extras on here just in case you guys needed it. Let's take a look at this one. Let's say we're trying to go from this blue figure and prove that it is going to be congruent to this red figure right here. What would be the single thing that we could do to go over and do that? It appears to be a rotation, and we always go counterclockwise. How many degrees does that look like it is to get on there? 180. That is all it is. You can do a single transformation and it'll sit on top of itself. That's it for that one. Let's do one more. Let's do, let's get this green figure on top of this. What other colors do I have? Yeah, yellow figure. Okay, how do we go from green onto red? Well, there are infinitely many ways to do this. Do you guys want to do a reflection first and then shift it? Do you want to shift it first and then reflect it? What do you feel like doing? Reflect first? Okay, let's first do a reflection, and we're going to reflect. We're going from green to yellow. We're going to reflect over which, see, this is a little funky. What do you want to reflect over? That's a fantastic idea, actually. Okay, so he says, let's reflect it over x equals -1/2. And the reason he did that was he saw that we had to shift. If I reflect over a full 1, then it's going to push it all the way over here. But if you do it over -1/2, then all you have to do is translate it, and you have to shift it directly down. He made it nice so that you could shift it directly down. And how much are we going to have to shift it down by? 1, 2, 3, 4, 5. Shift it down by 5, so over by nothing, down by 5, and that will put the green on top of the yellow. Does anybody have any questions on that? Okay, I just want to take a look at this one right here. This one has a dilation as part of it, and we're going from G blah blah blah, that looks to be the small one, to the big one. The reason I want to do this one with you guys is the book really likes to have their dilation centered at 0, 0, and I'm not a fan. I like to go over and just match up a point with its corresponding point, like do a translation over there. That way I can do my dilation centered at that point. So this appears, I don't know why it's not showing this axis. Weird. Okay, what is the first thing we need to do to get the small one onto the big one? We can do many different things. Do you guys want to make it bigger first, or do you want to reflect it first, or do you want to translate it first? What? Okay, make it bigger first? Great. What is a good location that is a pretty point already that we can go over and dilate from on this smaller triangle? Which one is a pretty point? Point F, G, or S? I like F. Doesn't F look like a nice point? Okay, let's do a dilation. Let's center it at F, and we need to figure out how much bigger we need to get. Ugh. See, are any of these sides easy to figure out the length of? Okay, so this rotation. I think that we might need, let's go ahead and try to do what the book is wanting us to do. The book wants us to reflect first. Let's see if we reflect first, if the points line up so that it's a nice, easy dilation centered at 0, 0. So let's go over and reflect over which axis? The y-axis. If I reflect over the y-axis, it is currently 2 over. It's now going to be here. That's where f prime is going to be. So f prime is at, what is that location? Anybody know? Does it appear to be 2, 2? Okay, 2, 2. And what is its corresponding point? The corresponding point is Q, right? Q's at 3, 3. Hey, look at that. That's nice. Okay, is this a dilation centered at 0, 0? Yes, it's either going to be 2 over 3 or 3 over 2. Since it's getting bigger, which one makes sense for our problem? 3 over 2. Okay, so the book was just trying to be nice and said after you reflect, it will be perfectly nice to be able to be centered at 0, 0. So it's a dilation scale factor of 3/2 centered at 0, 0. And that, when we do that, it actually we don't even need to do a translation because it's going to push the point on top of the other one. Does that make sense? I want to make sure you know, take a look. What I do on a lot of the homework problems is I will go over, let's say I need to do a dilation. I will map, since like, let's say A needs to be matching up with D, I'll go over sometimes and map the A on top of the D, and then I'll grow it from the D. Most times I do not dilate centered at the origin. I'm not a big fan of it. So what you guys are going to do on your homework is do these problems. It's saying, try these instructions out and figure out which ones are actually proofs to map ABC on top of DEF. So I want you to try this one and see if ABC gets on top of DEF. Then try this one and see if it gets ABC on top of DEF, and so on. Does anybody have any questions on this? It's basically, if you can use isometries to get on top of it, they're congruent. If you can go over and do isometries and a dilation, then they're similar. Questions on that? All right, we're done. Thank you.